Hello, my name is Tereshkin, and this is a talk about bypassing personal firewalls. We are trying to show here the principal weakness of the current firewalls against the Rootkits. Initially, we will briefly discuss Windows NT network subsystem, and we will move to some cheats afterwards. We will break some common techniques that most firewalls are using these days, and then we will go to most sophisticated level and discuss the real hardcore there. Finally, we will discuss a few ideas about how to make firewalls resistant to the presented attacks. Ring 0 part of NT is logically divided into two parts, I mean network subsystem part. The TDI, the transport driver interface, and NDIS, network driver interface specification. Firewalls are hooking both of them, and we will go into details a little bit further ahead about how they do this. Let me explain what I mean when I say bypassing techniques. Here you see no any connection as to TDI or NDs here. We are just using some very well-known and quite dirty techniques to make the firewalls be confused. We can do it in two ways. We can try to do something to hide from the firewall, or we can try to do something to damage it. The hiding here is also just an illusion. It's just a code injection in the traced process, for example. And the damaging of firewall drivers is, for example, preventing them from loading by patching their entry points with XOR, EAX, AX, red, or something like this. So these techniques do not actually bypass firewalls, they cheat them. And they are either firewall implementation specific or take advantage of incompetence of a user. All common firewalls hook TDI and NDs now. They hook TDI to get the process name or the context of the process which tries to get the network communication. And they hook NDs in hope to protect from the rootkits or to protect from attacks targeted from data link layer to transport layer, because TDI hooks cannot prevent data link layer attacks. Also, it makes possible to hook unknown protocols traffic using NDs hooking techniques. For example, it may be used to switch system to the totally network stealth mode. Most modern firewalls can do this type of switching. Let us explain here how the firewall actually does TDI hooking. The firewall must perform the attachment to the devices like IP, raw IP, TCP, UDP, in order to perform per-process traffic monitoring. And to do this, it has two options. One is to use device filtering, and the other one is to use driver object measure function hooking, which also is called like IRP hooking. We are going to show here how to bypass both of these options. These techniques are too high level to pose an obstacle for a rootkit, because this type of hooking can block on the rootkits that are using kernel mode sockets interface. And it's possible to use our own TCP IP stack, a custom stack, which will be very different from original. Here, this slide shows the first technique which may be used by a firewall. It's filtering of the TCP devices or UDP devices. This way, firewalls installs itself as a filter driver, and if any driver like Rootkit 1 will try to get the pointer to the original TCP device, it will get a pointer to the last filter in the device chain, device filter chain. And if the rootkit will, if a rootkit try to send some IRP commands to this filter device, these commands will pass through every firewall hook and most likely will be trapped. And They will not pass to the original device. So the rootkit may find the original device to prevent firewall from catching it. To do this, it may walk the filter device chain backwards. It may do it by using undocumented field named attached to. This field is located in the divulge extension structure. When this field is null, it means that this device is original and it's not a filter device. Well, what about major functions hooking? It's time to use tunneling to find the original handler. MS-DOS time has ended long ago, and you may forgot what the tunneling is all about. So I'll explain it a bit. If we are sending a legitimate packet to the network, it must eventually get to the original TCP/IP code through all the firewall's internals. And the tunneling will help us to watch how the process happens. And we will catch the execution transfer to the TCP/IP. We have to make 6 steps to achieve our goal. First, we should walk the relocation information of the TCP/IP to store all absolute labels which are used by this image. All drivers must have relocation info, and therefore these major function elements will have data references in the driver image. So if you get a list of all absolute pointers in the TCP/IP driver, some of them will be our needed major function addresses. Then we will hook int1 in all IDTs existing in the system, and we will install ourselves as handlers of the int1. We will do this to catch all instructions that will be executed by a cached thread, which is going to call IO call driver to the TDI filter device. This way, no code patching is required because we will change just the PIOF call driver pointer, and we will check if this thread is going to call hooked TCP device or if it's going to call any other. And we will check only interesting thread which is going to call to the TDI layer. This technique is used by driver verify, for example, to trace every IRP which is going through the IO call driver to the system. The next step of tunneling is to understand the current state of the traced thread. When we trace the thread long enough, there will be 3 possibilities of situations. One is that a thread will come to one of absolute labels of the TCP/IP driver. This means that that we just found the original major function address, because finally a thread must get through the firewall internals and get to the TCP/IP if this packet is allowed to come to the network by the firewall. The next possibility is that a thread will go to Intel's kernel.exe into the IOP invalid device request function. And this will mean that the called major function is not specified by the TCP/IP device. And the last possibility is that a caller of IO call driver simply returns without going into the TCP/IP or into kernel. And this means that TDI filter has denied something. A firewall has denied something. So we should wait for another IO call driver this way. If we get the first case, like if read has come to one of the absolute labels of the TCP/IP, we will remember this address and clear the trace flag in this thread. And after that, a rootkit will be able to call the original major function directly without using probably hooked IO call driver. And this way, it will make its calls not involving any firewall internals. But it should adjust IRP stack locations manually. And the last step of the tunneling is to unhook all IDT entries and finish the tunneling process if at least needed major function entries have been found. Let's move to ND's hooking. The hooking of NDs is performed by a firewall by hooking the ND's register protocol and this open adapter and these other two functions. This is done to catch all known protocol registration and protocol bindings. Common techniques used by a firewall to hook the ND's driver are these. The first one is the export table patching, and the other one is ND's code patching, which means direct code patching. This type of hooks are not a problem for a rootkit because there exist many ways how to remove these hooks, or even how to bypass them without altering any firewall internals. A typical scenario of registering a protocol by a rootkit or any protocol driver is this. First, this driver should call ND's register protocol. This way, it informs ND's that a new protocol is going to be registered, and later it may be bound to some specific adapter. So the firewall checks for known protocol name and maybe even this name will maybe a TCP/IP, for example, and it patches the given protocol characteristic structure with its own handlers. Then, when a driver will call ND's open adapter to bind its protocol to the specific mini port, a firewall should catch it, and it will patch the ND's open block structure, which is returned by the ND's open adapter in the ND's binding handle argument pointer. And this structure, it will patch send handler, send packets handler, and few other fields with its own handlers. In these handlers, the firewall should check the incoming and outgoing packets and deny it, and use some rules for the packet checking. It's a good idea to register a protocol which will not be noticed by NDI's hooking firewall, but for existing rootkits like DeepDoor or Elegrosso, which are going to hook ND's open block of a certain protocol binding, it's not possible. They use a technique of repatching firewall handlers in this open block structure. This may work for simple firewalls, but advanced ones will check their hooks for presence. So if we patch ND's open block directly, some firewalls may detect these hooks and they may set them back or just inform a user that there's some kind of a rootkit in the system. To leave hooks intact, but to register a file rootkit protocol, we may use some passive anti-hooking techniques to be sure that no part of a firewall will be modified. As I mentioned before, the techniques that firewall may use to hook NDs could be either export table based or direct code patches based. As for export table hooks, they may be defeated by finding original API addresses in the ND's image driver. Direct hooks may be defeated with the code pullout technique, which I'm going to discuss later. The first technique used by firewalls is export table hooking. And to find original functions, we may use these methods. First, we load the ND's driver from the disk and map its sections with a custom PE file loader. Then we just walk its export table to find all needed relative virtual addresses and apply found RVAs to the original ND's image. And then the rootkit may call functions directed by a pointer and not relying on any import table anymore, because the import table is hooked. The last thing the rootkit must check is the direct code hooks, because even if the rootkit somehow finds original functions addresses, these functions may be hooked in the ND's image code. So the other solution for overcoming ND's hooking techniques is this. It's possible to use a totally new ND's image so that no code, so that we may be sure that no code will be patched there by a firewall. To do this, we load this image from the disk with ploader like in the previous solution, but we fix all absolute pointers which of this image to the existing ND's.sys image, because we want our new hook-free code to use existing ND's data. We're just cloning the code, but we leave data pointers in original state. The advantages of this method is the initialization speed, basically, because it's very simple, so we can perform few operations and it will work pretty fine. And other advantage is that the loaded code will be always correct, because it's just a simple clone of the running ND's driver. This technique is portable because we don't need to implement some kind of a disassembly engine and the PA loader for every processor which current operation system supports is also not needed to be implemented. The disadvantage of this solution is the used code size of the generated image. We are going to use only a few functions, but we load the whole ND's driver. And this code is identical to the original ND's. And if some kind of memory scanner will check for duplicates of driver's images, it will find that actually there exists two copies of ND's driver in the memory, which is strange. And now the code pullout engine. It's a more intelligent solution. The idea is to build a sufficient ND's code subtree. We should fix all absolute pointers to the existing ND's image as it was done in the previous solutions. But the main advantage of this solution is that the generated code size is much smaller than the full ND's image. Let's say it's about 30 kilobytes of code for these four hooked functions, which I mentioned before. The four functions like ND's register protocol, ND's open adapter, and two others. When we will generate a code subtree, this code may be mutated with any polymorphic algorithm, and this means that all code signatures will be broken. And if some kind of memory scanner will try to detect ND's copy, it will fail. The disadvantage is that the main disadvantage is that this engine is architecture dependent. For every supported architecture, it's needed to implement a code coverage and rebuilding tool. So I said about advantages and disadvantages, but actually I didn't say anything about the details of this solution. So the next two slides are about the details. To build the code subtree, we just need to perform a simple coverage of the code and rebuilding the covered code. To do this, we will just walk our entry points, and original entry points will be defined as relative virtual addresses of the needed APIs. When we will walk them, we will stop on execution transfers, like unpredictable control transfers like jump rec32, or any kind of returns like read, iRead-D. These types of instructions will mean that we come to the code that has been already analyzed. This will mean that our branches has just ended. And if we come to code that has been already analyzed, we stop our walking and take another branch to analyze. As for calls and conditional jumps, they actually fork execution flow. They add branches to later analysis. A subtree coverage map is complete when there is no more branches left in the analysis queue. The final steps of code pullout techniques is to rebuild all generated code to make it be possible to run. We have to recalculate entry points for the addresses which were specified as the top of original code subtrees, because the addresses have changed since we are going to move our regions of covered code we should relink all relative jumps and calls in the generated code because they have been broken when we moved all covered regions to the one big piece of code. That's because all relative instructions that connect non-adjacent code blocks were damaged. And the final step of the algorithm is to fix all relocations to the original and this image. After these steps, we will have generated code, which will be much smaller than the whole and this driver, but it's absolutely hook-free because we used original driver image from the disk and not from the memory. Okay, we've discussed a few tricks about bypassing simple firewalls, and then now we'll move to modern ones. These firewalls, in addition to the discussed techniques, new firewalls will check these open blocks structures for code pointers integrity from time to time. And this way, deep door and Peligrosa rootkits may lose their hooks because they just repatch the original firewall pointers in these structures, like in this open block and this protocol block. Let's see how modern firewalls perform protocol walking. They register a temporary protocol, and this way they get a pointer to that points to somewhere into the list, which is called in this protocol list. But this registered protocol will not actually point to the head of the list. It will not point to the head. The head of the list, which is called in this protocol list, is not exported. And the other thing is that there exists a spin log which protects the list of protocols from synchronization issues, and it's called in this protocol list log. And this log must be acquired when a firewall walks the list, otherwise a race condition may occur. But none of current firewall acquires this log. Furthermore, none of firewalls now searches for the this protocol list head. They just register a temporary protocol. So this solution is not absolutely safe because when they walk in this protocol block list using the next protocol link, one of these links may be broken because they didn't acquire the this protocol list log. So what about stable way for this problem? The right solution will be to use a real list head and real list log. The main problem is that they are not exported. Other problem is that this list is singly linked and we can't walk it backwards to find the head. But we can perform static analysis of this.sys driver to find all these variables because they are global, and it's easy to find them by walking this register protocol function. Both of these global variables are used by this function. So if we will enumerate all absolute pointers of this function, we will have a list of variables, and two variables from this list will be our needed ones. We will check every found global variable to be some kind of a pointer to a spin log by examining the calls to kf require spin log function. And actually, there exists just one variable which is used as a spin log pointer, and this variable will be our needed spin log which protects the list of protocols, and it's called in this protocol list log. Then we will acquire this the spin log And after that, we will try to walk every other global variable found in by the static analysis of the this register protocol function. Here we will use some tricks to check if this variable is actually a pointer to the list of this protocol block linked list, or it's a pointer to somewhere else. By looking into by checking some critical fields of in these protocol blocks, for example. This slide is about usages of in this protocol list global variable. I've shown here a few functions that use this pointer, but you see that none of these functions belong to packet indication code. The conclusion of this slide is that this global variable in this protocol list is not used by the packet indication code at all. So let's see how this open adapter actually registers a filter to the packet indication code. First, it should update a corresponding miniport filter database. The filter database is located at the xfilter structure, which is addressed by 4 fields in the miniport structures. The miniport structure is called in this miniport adapter, this miniport block. The xfilter structure has one interesting field called the open list. This is a list. This is a single linked list of x-binding infrastructures, and these structures are actually contain our pointer to the just registered in this open block. So you see that this does not use and this protocol list to find an open binding on any network event. But firewalls think that and this does so. Firewalls walk their list of protocols in assumption that every protocol which will be found in the list can get packets to from the network, and the known other protocols can get the packets. So you see here that and this saves information about bound in this open block in the particular in this miniport block using a direct pointer. And to manage received packets, packet indication code will call these 2 functions, ETH filter DPI indicate receive packet or ETH filter DPI indicate receive. The second one is for legacy miniports. And then the packet managers will walk ETH binding info list, and you see that and this doesn't care about and these protocol blocks here at all. Therefore, and this may indicate packets to the protocol which is not present in this protocol list. So it may be just excluded from this list after registration. But if this protocol is excluded from this from the protocol list, a firewall which walks this list will not notice this protocol, so it will not be able to hook it. There are 4 approaches to bypass firewalls that use protocol walking techniques. These approaches are targeted to somehow cheat firewall and register a protocol that will be not present in this list, protocol list head. First approach is use code pullout and some kind of direct kernel object manipulation methods. And the other two will not use any protocol registration. They will just hook existing ETH binding info or register a new ETH binding info structures manually. The first approach is about protocol unlinking after the registration has succeeded. First, a rootkit has to unhook and this registration protocol and this open adapter functions. And after the unhooking has finished, a rootkit will have to call these hook-free APIs to register and bind the protocol. So this protocol will exist in the ND's protocol list. But then rootkit unlinks this protocol because it already knows the ND's protocol list head, and the information about address of ND's protocol list head is required here because this list is single linked, and we cannot find the head of the list by working the list upwards. The major shortcoming of this method is that Firewall may detect and hook newly registered protocols before we unlink it. So this solution is easy to implement, but it's not practical. The second approach is about modifying our copies of ND's registered protocol and ND's open adapter. So they will look just like original functions, but our copies of these functions will address a different list head of the protocols, which will result in registering a protocol into a different list. So if we have a protocol which is registered in a list different than original and this protocol list, a firewall will notice nothing when it will check the list after the registration. This solution uses disassembler engine, so it requires, so it's not easily portable. And the other thing is that it requires to hook receive handlers of all other protocols bound to same adapter. Because we don't want our packets to come to original TCP IP stack. Other protocols may be hooked by a firewall, and we don't want the firewall to receive these packets at all. Next solution is to patch the X-filter structure. We will find the X-filter list by looking into the ND's miniport list, miniport block structure for example, Ethernet data link layer. We will choose random protocol binding to the specific adapter by working its open list links. Then we will make a copy of NDIS open block, which we choose randomly, and then we will patch all needed handlers in this open block and substitute a pointer to the original in this open block for the pointer to the patched copy. So this will result in tricking the packet indication code so that when a new packet will come to this code, the indication functions will use our and this open block structure instead of original. So this solution is very stealthy because it requires only one pointer modification. And the integrity protection driver, for example, should check the X-filter for a single pointer modification. This will result in lots of false positives. The last approach is about emulation of the NDIS API code. If we register our own ETH binding info or X binding info structure without any original system code, we will be sure that no firewall has caught the registration because we don't use any system code to do this. The major shortcoming of this method is that it's very NDIS version dependent. So the receive packet techniques are more or less clear now, and I'll move to stealth packet sense. For the first two solutions, packet sending is trivial because all our structures, like in this open block and in this protocol block, are not hooked by firewall. So we may use pointers from these structures, and we may be sure that these pointers are not hooked by a firewall. Actually, the sending packet functions are defined in these with similar names, like in this msendx and other ones. I show it. And these pointers we get from the send handler pointer. By the way, these APIs may be hooked in this image, so it's a good idea to use code pullout again. But we may not change any relocations because we will use original in this code. The third solution requires a different method of sending packets silently because actually we didn't register our own protocol, and the original protocol which we have hooked before may be hooked by a firewall, so we can't rely on a send handler or send packets handler pointers anymore. So there are three possibilities how to find original functions which may send packets to the network bypassing any firewall installed. We may find these functions by tunneling the firewall, or by searching in this image, or by temporarily registering and binding dummy protocol. And this protocol registration should not be called by a firewall because we have to find these functions and these msend and others, and we don't want to get these functions hooked. So let's move to the demo. I prepared the VMware installation with two popular firewalls. First is Zone Alarm, and the other one is Outpost. You see that a network is not trusted, and by default the firewall should ask a user about every suspicious packet which comes to this network and from it. Let's install a rootkit. First I show the solution number 2. Here you see the process of registering a protocol silently. First we should find in this protocol list head, and we performing this by walking the NDIS register protocols tree. First we find spin lock, protocol spin lock, and then we acquire it and walk the list to find the original registered system protocols. But here first we check for valid pointers to the in this protocol list, and we don't want to use pointers that do not point to this protocol list head. Then we ripping the code of this driver and patching all the references to this protocol list to other list head, which was allocated by us. Here you see that anti-hooking has succeeded, and it just generated 30 kilobytes of code instead of, for example, 100 kilobytes of original in this image. Then we move to protocol list and iterating through the protocols which are registered in it. We bind our custom TCP stack to the IP which is not used by the original stack, and then we start a FTP server. So let's try to see how it will operate when we stop all the incoming and outgoing traffic in the zone alarm firewall. I should mention here that to install a rootkit driver, I disabled the driver installation controlling functionality in zone alarm by myself. So it will not ask me when a driver is being loaded. Okay, so now I connect to my FTP server from the original box. And you see that even if we blocked all incoming and outgoing traffic in the zone alarm, I still can read the directory of the system. So I could download and upload any files. This happens because we hooked network subsystem below the zone alarm itself. The third approach, as you remember, was about hooking X filter structures. As you see, it's a bit easier to understand what is going on, because we don't lock any and this image code. We just hook the randomly chosen X binding infrastructure here, and you see that both rootkits are run simultaneously. And if you try to connect to other FTP server which is run on the original IP of the original TCP IP stack in the system, it will succeed too. So you see that both rootkits are run on different IP addresses, and one rootkit shares the IP address with the original TCP stack of the operation system, and the traffic settings in the zone alarm are set to block any incoming and outgoing traffic. So let's continue with presentation. The last thing I should mention is hardening firewalls against these attacks. You see that a firewall should operate at a more privileged level than a rootkit, because if a rootkit is run in kernel mode, it will be able to patch any protection which is introduced by a firewall. So the only solution for firewall vendors is to complicate their solutions, their firewalls. So maybe a full rewrite of this driver is a good idea. What about monitoring packet receives? A firewall may find unlinked protocols by walking the X-filter list in this miniport block. And this is actually how this packet indication code addresses registered protocols. And it's not using this protocol list, actually. For sending packets, this is not so easy to do because a rootkit may not use its send handler, but it can call these msend functions directly. So a firewall should at least hook code of this msend and whensend functions in hope to catch any packets sent by a rootkit. But this is not a safe solution. The nature of packet send interface does not require any special system object registration. So it's possible to send packets which will be not called by any firewall, since this behavior doesn't like to be changed in the near future. Thanks.